So, hello friends. Today I'm going to discuss about the Heisenberg uncertainty principle for single slit diffraction, and we'll try to see if single slit diffraction can satisfy the Heisenberg uncertainty principle. And it's the idea is very intuitive and it's very easy actually. So before going to that, first I want to show you what the single slit diffraction is really is. So obviously I'm not going to do the experiment, but there is online simulation tool, is very popular simulation tool called Phet, Phet, and I'll provide the description link in the description for this experiment. So on your screen, if you see, I have a laser here, and then I have a slit, then I have a slit here, and then I have a screen, right? So as I turn on this laser, for this slit, you see a diffraction pattern, right? On this right side, and then here your slit is. So now let's now imagine if I increase the slit width, what's gonna happen? Focus on this central lobe, the central part. So if I increase the slit width, now you can see the width of the central part on the screen, central lobe starts to decrease. And if I reduce the slit width, then that same central lobe starts to get wider and wider and wider, and whole diffraction pattern actually becomes wider. So now this is like little bit hard to grasp actually, like it's little bit counterintuitive. I tell you why. Because imagine this slit is just a window, right? It is just an opening for the light to cross. But now you can imagine, if light would be a particle. Let's say there are bullets coming. Particle is just like a bullets, right? If you are throwing bullets or if you're throwing stones at this slit, then on the other side of the slit on the screen, you just see small spots in a confined space. And if I keep on reducing the slit width, the spots should be localized around the center more and more. Rather than localizing around the center, the light now actually is getting wider and wider and wider. It's spreading rather than localizing in a small space. So it's very counterintuitive. As you decrease the slit width, the diffraction pattern becomes wider. So that's actually really is the uncertainty principle at play. So I'll show you how. um, so actually the description that I'm going to show you is from a paper, from a research article, and the I will provide the link for that article in the description. And it's again the single slit diffraction experiment. And here you see that laser again, and a slit, and and a screen. On the screen you have a diffraction pattern. And the diffraction pattern is actually having a central maximum here of width of some width. And then you have a slit. Let's imagine the width of this slit is d, right? So the width of this slit is d. Now what we're gonna do, I'm gonna I want to show you if it really satisfies Heisenberg uncertainty principle or not. And the definition of Heisenberg uncertainty principle that will be applicable over here is the same good old formula that we know. But notice here, I'm using the one-dimensional case of Heisenberg uncertainty principle. Why one-dimensional case? Because the momentum, I'm taking the x component of momentum for the for I'm taking the component of momentum now. Um, and now here is really x component, because this is little bit tricky. The momentum is actually the tricky part. The slit width is the position is quite easy. So imagine you have a slit, right? Imagine you have a slit of width d, and then the screen over here. You have screen over here, and now first we're going to calculate the uncertainty in position and uncertainty in the momentum. So this uncertainty principle I am applying at the slit location, actually at this location. So first let me introduce my coordinate system. This is x direction, and let's imagine the forward direction is z, right? Imagine my beam is, or is going in this direction. My photons, the photons are coming in this direction, or my beam is going in this direction. Now again, as I told you before, the slit width is d, right? The slit width is the slit width is d. And now imagine you have a photon coming in, you have a photon coming in, and this photon, the whole beam is coming in over here. But what happens, let's pick an arbitrary photon, right? The photon can be, that arbitrary photon can be anywhere between the slit, right? So so the uncertainty actually, so the will be uncertainty will be, we can say, the position of photon will be localized between these two limits, right? Minus d by 2 to plus d by 2. The photon can be anywhere between the slit, right? So the uncertainty in actually, the uncertainty definition that we are taking here is actually what is the possible what is the difference of minimum and maximum values that we can think of as uncertainty. So uncertainty will just be of the order of slit width. That's that's not easy, that's not hard to imagine, right? The photon can be anywhere in the slit, so uncertainty will be of the order of the slit width, right? And now let's um, focus on the momentum part. So this was my photon, and that photon, now let's imagine this is my central diffraction maximum. Now please don't go into my drawings, and also I'm just, for the sake of application, I'm doing a little bit of exaggeration here. And so this is my central diffraction maximum. Now what we are going to focus on, we are going to focus on the direction part of the momentum. The uncertainty is coming from the direction of the momentum, not from the magnitude. So the definition of photon that we're taking here, P is equal to h cut k, right? Where k is the k represents the wave vector, or the wave number, and with the associated direction. Or in other words, you can write it as h upon 2 pi, with k cap as the unit vector for direction. So um 2 pi lambda, yes, sorry, h upon lambda, sorry. So p is h upon lambda k cap, right? So um the this is the magnitude is h by lambda, the good old de Broglie magnitude that we know, and then the k cap will focus on the direction. So now imagine you have this photon, right? Now this photon can be anywhere within this central diffraction maximum, right? And as we did before with the position, now what we want to know, what are the minimum and maximum values for the x component of momentum. So for now I talked about the component, so it means we need to first introduce the vector, the momentum vector. The momentum vector you can think of as, let's say, this photon goes um, somewhere in this direction. Let's say this photon goes somewhere in this direction, right? And then let's imagine this is the central axis and it makes an angle theta. So let's say this is my p vector, right? So now we can resolve this p vector into two parts. P can be p cos theta and p sin theta. So the pz, actually the z component will be p cos theta, and the x component will be p sin theta, right? Right. And so as I told you, so you can think of it as pz here and px here, and this is my p vector, right? So we are interested in the in the x component, right? We are interested in the x component. So the x component will definitely be then px p sine theta, right? And we are interested in the maximum and minimum values of this x component. So what would be the maximum and minimum values? So the maximum minimum values, if it's not hard to imagine. So let's focus on this. Is, I told you, the maximum at with what angle in this um, central maximum, the maximum angle that photon can go is, let me take it out. The maximum angle that photon can go is to the edge of the central maximum. After that, there is dark region start. The dark region starts afterwards. So the maximum it can go to the edge of the central maximum, and the edge, the what's the angle that it can make? Let's say it makes angle again. I call it theta. Then now this is a theta. You can choose to call it, yeah, I call it theta. This angle as theta. So now you can see this can be p, the maximum value of the x component then will be what? P sine theta. Let me remove the z component as we are not interested in this. So the maximum value will be p sine theta. And similarly, the minimum value will be in the other direction, right? The minimum value will be what? Correspond to minus theta angle. For similarly for theta, you have minus theta here, so it will minimum will be minus p sine theta, right? So the uncertainty in the x component is again the difference of maximum minimum values is of the order of 2p sine theta, right? So let's just put it back into the equation. Let's just put it back into our Heisenberg uncertainty equation. Delta x, we got to know delta x is over this, and delta px is again this, right? So delta px greater than h cut by 2. If I rewrite it, it should become d times 2p sine theta should be greater than h cut by 2, right? So now p, as we discussed before, p is h by lambda, right? So d times 2p h by lambda sine theta should be greater than h cut by 2, right? So now the what is remain to be proved is what is the value of this in sine theta. Here comes the the, the smart part. The sine theta is actually, if you can imagine, this sine theta is actually the dark, where the dark region begins. So it is the position of first minima, right? It is the position of first minima. And uh, what is the condition for first minima is, the condition for first minima, we know the diffraction condition. The diffraction condition for first minima is again the good old theory that, you divide the slit into two parts, and then you say half of the slit will interfere destructively with the other halves. Then you arrive at this condition: d sine theta is equal to m lambda, and then for m equal to 1 you get the first minima. So then d sine theta is equal to lambda, right? So this is the condition for first minima. So from here we can write sine theta is equal to lambda by d. It is very easy now. Let's just combine these two numbers again into lambda 2h. We use the, so 2h by lambda into lambda greater than h cut by 2, and then lambda times, it's really, you have 2h greater than h cut by 2. So on the other side you have actually h upon 4 pi, right? H cut is h by 2 pi. So you have this, obviously 2h will be greater than h by 4 pi, but like whatever way you want to consider it. So then what you say, then I'll say hence proved. Right? So you can see here single, very easily you can prove the single slit diffraction satisfy Heisenberg uncertainty principle. And it's just the wonder of one wonderful thing that light, it tells you that the light follows the wave particle duality. Very nice to see. And actually in the paper that I'm going to put, they also verified it experimentally. They measured they did this real experiment, and they changed the slit width and calculated verified the uncertainty principle with the experimental values for different scenarios. So yeah, so this is it. Thanks guys.